Yeah.
Okay, the next speaker is Dr. Bak Chan from IBS. The title of talk is Observation of a Gravitational Wave by Invariants for Electromagnetic Waves. Please.
Okay, thank you. Hello, everyone. First of all, thanks to Professor Dong Yam and all organizers for organizing this workshop. Today, I will talk about a novel method to observe gravitational waves using electromagnetic invariants. Okay, let me start. I would like to briefly introduce the detection of gravitational wave by electromagnetic wave. There are many origins of gravitational waves, but due to the performance limit of modern gravitational wave detectors, the gravitational wave we can observe are limited to the one generated by binary compact stars. Compact binary emit gravitational waves, and gravitational wave is propagating over space-time. When it meets our laboratory, we have prepared an electromagnetic wave between a source and detector. And there are two kinds of gravitational wave detectors using electromagnetic waves. First one is interferometer using high power laser with wavelengths of about 10 to the 3 nanometer. The photo detector accepts electromagnetic wave. The typical size of a detector is about kilometer, and its target gravitational wave source is about 10 solar mass binaries generating gravitational wave with frequency of 10 to the 2 Hertz. And LIGO, Virgo, and Kagra are internationally cooperating to detect gravitational waves. The second kind is pulse timing array. The source of electromagnetic wave is electromagnetic pulses from a pulsar. Each measurement is made by radio telescope having frequency band about 10 to the megahertz. And typical distance to pulsar in our galaxy is about kiloparsec. And its target gravitational wave is a stochastic source of a frequency over 10 nanohertz from binaries of supermassive black holes in cores of galaxies. And nanograv EPTA and PPTA are representative pulsar timing arrays to detect the stochastic gravitational waves. There are many theoretical works required in gravitational wave physics. First, we need understanding on dynamics of gravitational wave source. This phenomenon usually have high energy and high gravity, so gravitational wave detection is an arena of models in high energy physics. In the propagation, gravitational wave experience gravitational lensing effect by massive objects. Gravitational lensing of gravitational wave is also very interesting topic that can be observed in modern gravitational wave detectors. And electromagnetic wave is perturbed by gravitational wave, and by measuring it, we can extract information of gravitational waves. The main theory to analyze this effect was developed at 1980s. The modern gravitational wave detectors are based on this old theory. So I think the theory should be updated and extended. So these two topics are my main research topic that will be introduced in this talk. And data analysis is a very active field in gravitational wave physics, and my research also includes data analysis method, but I will discuss about this in this talk. This slide shows motivations of my research. Modern gravitational wave detectors, including PTA, pulse timing array, and LIGO, are based on geometrical optics of electromagnetic waves. The geometrical optics require a clear distinction between gravitational wave frequency and electromagnetic wave frequency, where omega E is the electromagnetic wave frequency and omega G is the gravitational wave frequency. In geometrical optics, Maxwell equation is simplified to the null equation, but I would like to give a full wave optics solutions of Maxwell equation without assumption of smallest of omega g, then omega e. My analysis can be used to extend the capability of modern gravitational wave detectors or design novel gravitational wave detector to detect ultra high frequency gravitational wave. Let me introduce the electromagnetic invariance and its advantages as a measured quantity. We learned classical electromagnetism in the undergraduate course, and F is the electromagnetic field strength tensor, that is 4x4 anti-symmetric tensor. The field have two invariants, I1 and I2, defined by these formulas. They are scalar and pseudo-scalar, respectively, that do not depend on any observer. And if we have an observer with pole velocity n, the field strength tensor is decomposed into E and B field, like this. As you know, E and B depends on the choice of observer, but invariant can be determined from E and B using these formulas. Although value of I1 and I2 are determined from E and B of a specific observer, but they do not depend on any observer. For plane wave propagating direction, we can easily see that their invariant vanishing. And now I propose the invariance as measurement quantity in gravitational wave detectors. There are many advantages of the invariance as a measurement. First, we do need consider an acceleration noise that comes from the Earth's motion relative to our galaxy. For example, measurement of tensor component in a red frame suffers acceleration noise in principle. But we don't need to worry about that for scalar quantities. Secondly, the invariant has zero value when absence of gravitational waves. Measured quantity consists of background value I1 and each perturbation Ji. When there is no gravitational wave, we only measure background value I1. When gravitational wave is passing, perturbation induced by gravitational wave is superpositioned to measured quantity. In our case, background value is 0. The perturbation of zero value quantity is more easily measured than the perturbation of non-zero value quantity. And thirdly, the perturbations of invariants are gauge invariant. Simply speaking, theory guarantees that we can observe them without any ambiguity. Let me introduce a naive sketch of measuring the invariance. For the moving straight conductor with the length vector L and velocity vector V, electromagnetic field induces electromotive force given by this formula. If we measure electromotive forces from 6 independent wires, we can determine E field and B field. Then the invariant of measuring the invariant can be determined if invariant can be determined these formulas. The feasibility of measuring the EM invariance requires further discussion with experimental physicists. Let's move to the theoretical part to calculate the perturbation of electromagnetic invariance. And to keep your lunch time, I will skip some slides. The EM potential has leading the value A and its perturbation X. And the Maxwell equation in the leading order becomes the homogeneous wave equation with Lorentz gauge. The Maxwell equation in the next leading order becomes the wave equation of X with source terms that consist of interaction terms between gravitational wave and electromagnetic wave. We consider a plane electromagnetic wave having this form, where C is a set of null vector, but I will skip this slide. And this is the general setup of gravitational wave. And I used this gauge condition, but I don't know how to call this, but I just call it double null gauge. Notice that the amplitude of gravitational wave, this comes from the Lorentz gauge, but we impose another vanishing condition with null vector L. L is the null vector of electromagnetic wave, and K is the null vector of gravitational wave. Then Perturbed Maxwell equation becomes simplified into this equation. In general, we have 4 terms, but in this case, we can eliminate many terms in the source term. So it reduces much labors to calculate in calculation. The solution of this wave equation with source term is the superposition of a particular solution and homogeneous solution. And particular solution is determined by a source term in the wave equation for X. The homogeneous solution is determined by a boundary condition. Okay, let's skip. As a result, we obtain general solution of perturbed invariants like that. And let me give a visualization for the perturbation of EM invariants. For simplicity, we consider a monochromatic plane electromagnetic wave, where tilde E is the amplitude and Q is the phase. The phase is a function of space-time, where omega E is the frequency, and lambda is the unit spatial vector of propagation. Every complex amplitude E can be transformed to this form by adjusting constant phase alpha, such that real part and imaginary part are orthogonal to each other. And then where curly E is a strength of amplitude, and a set of PS lambda forms a right-handed orthonormal frame. And because real part of amplitude sweeps the polarization ellipse, so chi is actually the ellipticity of the ellipse. And in general, the ellipse is tilted our arbitrary coordinates like this diagram. And I give an analogy of electromagnetic wave to get a standard form of gravitational wave amplitude. We consider a monochromatic plane gravitational wave, where H tilde is the amplitude and P is the phase. The phase is a function of space-time, where omega G is the frequency, and kappa is the unit spatial vector of propagation. And it also every complex amplitude H can be transformed to this form by adjusting constant phase beta, such that real part and orthogonal parts are orthogonal to each other. Where curly H is the strength of amplitude, and E plus and E cross are defined by U and V, such that UV kappa forms right-handed orthogonal frame, and eta is defined its ellipticity. This animation shows effect of gravitational wave to test particle for each polarization. Third one is a mix of two polarization and is propagating to kappa direction. I give you some magic. They are arbitrary. They are gravitational wave and electromagnetic wave propagating arbitrary directions and frequencies in observer. If we choose an observer carefully, we can always make EM wave and gravitational wave be propagating to opposite directions to each other and having same frequency. The observer's forward velocity v and propagation direction g is given by this formula. After solving linear system, we can identify that two waves have identical frequency and propagate to opposite direction to each other. And note that H tilde and A tilde, H tilde of gravitational wave and A tilde of electromagnetic wave live in identical planes spanned by PS or UV. In this observer, we can consider polarization angle of gravitational wave defined by angle of U with respect to PS plane. Integrating all components, we get the analytical result of JI, that is perturbation of invariance, electromagnetic invariance. And note that it is proportional to the strength of a gravitational wave. And we identify three modes that are P and P plus 2Q and P minus 2Q. And they have separate pattern functions depend on electromagnetic wave ellipticity chi and gravitational wave ellipticity eta and polarization angle of gravitational wave xi. And they are just factor determined by position of detectors. So we will not consider about this value. And because of symmetry of pattern functions, I only show F1 plus for several chi value. And A is the linear polarization of electromagnetic wave, and B and C are elliptical polarization of electromagnetic wave, and D is the circular polarization of electromagnetic wave. The polar angle represented in this frame, polar angle represents the polarization angle of gravitational wave xi, and azimuthal angle is the ellipticity of gravitational wave eta. And when electromagnetic wave is in the circular polarization, we cannot determine the polarization angle of angle xi of gravitational wave. Okay, let me summarize my talk. We propose an observational method for gravitational wave using invariance for electromagnetic wave. The invariance has many advantages in respect of measurement. And we provided the analytical result of perturbation of invariance. And because our analysis does not assume geometric optics, we can consider a detector using electromagnetic wave over any frequency to detect gravitational wave over any frequency. Our result can be applied to extend existing detectors and or design a new detector. And the feasibility of a method requires further discussion with experimental physicists. That's all. Thank you for listening.
Thank you. Question?
I have a basic question. So basically, so there is no direct interaction between gravitational wave and electromagnetic wave, but you are measuring gravitational wave effect by from the deformed space-time through the electromagnetic signal. Is that right?
Yes, that's
Right.
true. Every
But
modern gravitational
yeah.
detectors using the principle you mentioned.
Yeah, that's what I mean. Have you thought about some sensitivity problem, like as a LIGO? That was some crucial issue, whether it can be actually viable or not.
Yes, that's true. And my work is this talk is this work is preliminary work, and
Right.
I didn't consider noise yet. And actually, I didn't any experimental. I didn't consider any experimental setting to measure this quantity. So the noise analysis. Noise is a very crucial thing for gravitational wave detector, but it will be a future work.
Thank you.
Thank you. Yes.
Any other question? If not, then let's thank speaker again.
Yeah.
네.